AP Review, Lesson 11. In this final two lessons, we'll take a look at electrochemistry, which involves reactions that produce electricity, in essence. In this lesson, let's take a look at some multiple choice questions, and in the following, we'll do free response. Okay, so this first question asks about oxygen, and we're asked, oxygen is acting as an oxidizing agent in all of the following reactions except. Now, recall that an oxidizing agent is a substance that gets reduced. And the reason we call him an oxidizing agent is because he will oxidize the other substance, and he will do so by pulling the electrons off of it, therefore himself getting reduced. So what we want to look for is a reaction in which oxygen actually gets oxidized. So we need to see oxygen get oxidized. Now this is actually a rare occurrence because oxygen is the second most electronegative element on the periodic table, and oxygen loves electrons. So just analyzing the reaction itself, if for example you take a look at reaction E, let's just go from the bottom, and you see that magnesium here has a charge of 0. On the right side, magnesium has a charge of +2. Magnesium got oxidized, and oxygen, starting out at 0, gets a charge of -2. So oxygen gets reduced. So, and this happens again with sodium. This happens in most cases, except in the case of fluorine. This compound right here, fluorine, is actually sitting on the right side, and if you recall, fluorine is the most electronegative element of all. So between oxygen and fluorine, fluorine will be the one taking the electrons away. So fluorine is the only one that can beat oxygen, essentially. So in this case, oxygen actually gets oxidized. We go from a charge of 0 to a charge of +2, as is the case here. Fluorine goes from 0 to -1. So in fact, this C would be the answer. And so it's a good idea to understand oxidizing and oxidizing agents and be able to analyze a reaction for this idea. A different type of question, slightly different type of question. A 1 mole sample of zinc can reduce the greatest number of moles of which of the following ions? And this, if we were to balance zinc, now zinc will actually become zinc 2+. Here it says a zinc can reduce, which means zinc himself will get oxidized, and the question is, which ion can it do this the most to? Well, it'll be the ion. First of all, chlorine will not be reduced further, neither will nitrogen. These guys are already reduced, you can say, so it's between these three metals at the top. Now, if I were to add a silver, and take a look at what silver does, silver will get reduced, then go from +1 to 0, and recall that when we balance these, we would add electrons. So for the zinc, I would add 2 electrons here, and for the silver, I would want to add 1 electron here, to make sure that my charges are balanced. It's 0 on this side, it's got to be 0 on this side. Same thing here, 0 on this side, it's got to be 0 on this side. And then, as you put them together, you would have to multiply this whole half reaction by 2, so that way we transfer the same number of electrons. Well, that would mean eventually that we would reduce 2 moles of silver. And if you do the same thing with lead, you won't have to multiply by 2, so it'll reduce 1 mole of lead. If you do the same thing with aluminum, you'll end up multiplying zinc by something, which messes it up even further. So actually silver is the answer. Zinc can reduce the most silver out of these because he's a +2 charge and silver is a +1 charge. And that's kind of the idea. So be able to put these reactions together. Remember, when you put them together, then these cancel out. And finally, you just write zinc +2 silver, producing zinc 2+ plus silver neutral. And then this whole reaction is in fact balanced. So be able to combine half reactions. Next, let's take a look at the voltage that's associated with half reactions. And here it says, according to the standard reduction potentials given above, referred to these here. Remember, these numbers are what come from the reduction potentials table, which simply lists elements or compounds in order of their reduction potential. The ones at the top are the most likely to be reduced, or the ones that are more positive are the more likely to be reduced. So here, notice that we have silver being reduced, going from +1 down to 0, and aluminum being oxidized, going from a 0 to a +3. And then silver gets reduced. So recall that oxidation happens at the anode and reduction happens at the cathode. Now, in order to find out the voltage, the cell potential of the whole, the voltage of the whole cell, remember there was an equation that said like this: E of the cell, the potential E is the cell potential, or the voltage of the cell, is equal to the cathode minus the anode. So here, our cathode is actually our silver, and the silver here has a voltage of 0.80. This is our cathode then, this is our anode. So we'll do 0.80 minus the other one, which is negative 1.66. Now this will essentially be adding 0.80 to 1.66 and getting a final value of 2.46 volts, which is answer D. And recall the way to remember this equation. Now we will be given a set of equations, but think of, if you recall, in our voltaic cell, what we did is we went from the anode, electrons flow from the anode, this part is the anode, to the cathode. And so the voltage, or the path of the electrons, can be thought of as final minus initial, cathode minus anode, and that's the way to remember this equation. But if you want to know the voltage, remember these electrochemical reactions, the first thing they give us are this voltage, and that's essentially a measure of the difference between the two half cells' desire for electrons. Okay, let's go ahead and do this next one. This actually refers to the next three questions. So we have three half cells. Notice the half cells each contain a different metal. We have aluminum with the corresponding salt, copper with the corresponding salt, and iron with the corresponding salt. And galvanic cells are two of them mixed together. Remember, you have to have two half reactions to obtain an overall oxidation reduction reaction. Cell 1 and 2 in galvanic cell X. Galvanic cell can also be called a voltaic cell, recall. Voltaic cell. These two are synonymous. So we have aluminum and copper giving us a voltage of 2. We have aluminum and iron giving us a voltage of 1.22. We have iron and copper giving us an unknown voltage. And the first thing they'll ask us to do is actually to determine this unknown voltage. In fact, if you take a look at the next question, it says, what is the standard cell potential of galvanic cell Z, which is this one here. The easiest way of doing this is actually to recognize that the first two equations will add up to give you the third equation if you turn one of them around. So I'm actually going to flip around the first equation, and I'll put reactants where products are. So I've got 2 aluminum plus 3 reacting with 3 copper, giving 2 aluminum and 3 copper 2 plus. So I've actually just rearranged this equation. And now you'll see what will happen is the aluminum will cancel out with the aluminum, and this aluminum will cancel out with this aluminum. And notice what we'll end up with, do this in purple, is 3 coppers on the left side, copper 2 plus on the right side, and that is not what we want, is it? Let's see, did we do that? Yeah. Looks like what we want is 2 copper 2 plus on the left side. So what we did then is probably we should have left this one alone and flipped the second equation. And notice that everything lines up except they're on the wrong side. In fact, here the iron 2+ is on the right side and the iron is on the left side. So why don't we redo this? So scratch and second go. Let's go ahead and flip this equation right here. This will make it a little easier. So let's put the aluminum, 2 aluminum 3+ and 3 irons, producing 2 aluminum and 3 iron 2+. That should work a little easier. Okay, and now let's see if we line up. Notice my 3 aluminums still cancel out. These are out. My 2 aluminums still cancel out, and these are out. And now I do have 3 iron on the left side, which matches the iron on the left side. I have 3 iron 2+ on the right side, which matches. And I have 3 copper matches, and 3 copper 2+, and the copper matches. Now you may be saying, but we have only 1 and we need 3. And this is true if we were working with anything else, like delta H or delta S or delta G, but because we're using voltage, cell voltage, recall that we said that voltage is Coulomb per second. It's an intensive property. And an intensive property does not matter on or it doesn't change when the amounts change. So in fact you do not have to do anything to the cell voltage. And this is a very important difference between these measurables, thermodynamic measurements, and this voltaic cell measurement. So this is a good thing that we're reviewing this, so you'll hopefully remember this for the exam. But all that's left to do then is to combine these two voltages. Anytime everything else cancels out, we just combine them and we get a voltage of 3.22. Let's see if that's one of the possibilities. It is. We are good. We are on the money. How about this guy? In galvanic cell Y and Z, which of the following takes place in half cell 3? So let's go back and analyze our galvanic cell. Let me clean it up real quick here. So analyzing galvanic cell Y and Z, these two, it's asking for which reaction happens in cell 3. Now, half cell 3. Realize that each one of these reactions has 2 half cells. And because the one that's the same has to be iron, essentially it's asking us about iron. We know that in Z, in half cell Z, or in full cell Z, iron is being oxidized. And in Y, you'll notice that iron is being reduced. So we can say in Y it's reduced, in Z it's oxidized. And is that one of the options? Reduced in Y, let's see, reduced in Y and oxidized in Z. Is that what we saw? We saw reduced in Y, we saw oxidized in Z. So we have found our answer. And finally, we're going to be changing some concentrations and asking about the voltage. Now, here it says we have, if the half cell containing the iron. Now remember, anytime you have a little naught by the quantity or thermodynamic quantity, or in this case electrochemical quantity, this means that we are under standard conditions. And among other things, it means we have a 1 molar solution. So when we change that, our voltage will change. In fact, here it says that the iron is replaced with a 5 molar solution. In other words, we're increasing the molarity. And what will be the effect of the cell voltage of the two galvanic cells? Again, looking at Y and Z. Now for this, there's actually an equation. And the equation, let's go ahead and go back and do it off of the original. The equation looks like this. The cell voltage under non-standard conditions equals the cell voltage under standard conditions minus 0.0592 over N times log of Q. Now N is the number of moles of electrons transferred, And Q, recall, is like K, which is products over reactants. This cell voltage is cathode minus anode. And here they want us to take a look at it qualitatively. So what we do, let's take a look first at cell Y. In cell Y, we see that iron is on the solution is on the left side, on the reactant side, which means it all comes down to Q. For cell Y, if Q, since Q is products over reactants, when we increase the concentration, what we're doing effectively is we're increasing the reactant concentration. The top is still going to be 1, and the bottom now is 5. So 1 over 5 gives us a fraction, a number smaller than 1. Now anytime you take a log of a number smaller than 1, you get a negative. So this whole term right here becomes negative. Since we're subtracting a negative, overall we have a positive change, and the cell voltage overall goes up. So let's see if we can review that again. Because the reactant got increased, the Q, the reactant, is on the bottom side, so the denominator got increased, which means the whole fraction is now less than 1, which means the log of that is negative, because recall that tiny numbers like 0.01, which is 1.0 times 10 to the negative second. If you take the log of that, you're simply pulling out this number, so the log of tiny numbers are negative. You end up with a negative side right here on this term, which subtracted with this negative gives you an overall positive, and the cell voltage goes up. So in Y, the cell voltage will go up. In Z, the opposite is true. Iron is on the right side, so the exact opposite will happen, which means its voltage will go down. Take a minute to think through that. Analysis of an equation like this is very commonly done in the AP exam, especially when they want you to be able to use an equation, but they don't want you to spend the time to calculate it out, as is the case in this multiple choice question. So Y goes up, Z goes down is what we're predicting. And is that one of the answers? Voltage Y increases and Z decreases. That would be C here. And this should conclude for us this lesson of Chapter 20.